Okay, while people are joining, I'll go ahead and start introducing Shane so I don't take too much of his time. So it's my real pleasure to introduce Shane today to give this STS seminar. Shane originally obtained his bachelor's degree in mathematics with a minor in computer programming at Towson University. He then worked many different jobs as a software engineer, community college instructor, high school teacher, and also tried out for a professional indoor soccer team. He then went to graduate school, first to get an MS degree in nutrition at University of Maryland, and then his PhD degree in inorganic chemistry from Johns Hopkins University. He then went and did a postdoctoral stint at Caltech with Professor Nate Lewis until 2013. And at that time, he then joined UCI as an assistant professor and now an associate professor in the Department of Chemistry with joint appointments in the departments of chemical and biomolecular engineering and material science and engineering. In 2016, Shane was named one of the first 5 inaugural Moore and Mentor Fellows. He's also received a DOE Early Career Award, 2 UCI Beal Innovation Awards, and Sloan Research Fellow, Cottrell Scholar, Kavli Fellow, Scilog Fellow, and UCI Faculty Innovation Fellow. So he's been quite decorated for his work since he's been here. And I will hand it over to you.
Thanks so much, Jenny. Can you hear me? Awesome, great. Thanks for the introduction. Thanks for the opportunity to speak in this wonderful seminar series that started. This is a really new and exciting opportunity, not only for me, for the Department of Chemistry, for engineering schools, but for all of UC Irvine. I think this is a really just amazing program, and I'm honored to be invited to give a seminar here. So as my title states, and as was in my abstract, I'm going to be telling you about solutions that scale coming out of my laboratory that are related to combating global warming. And so the 2 stories I'll tell you today are related to removing sources of carbon dioxide and also providing sinks for them. Before I do that, though, I want to give you a very brief overview of my research group and what we think about as a collective whole under the umbrella of the words here: chemistry, engineering, and physics. And so this is a recent picture taken of my group, physically distancing outside, goofing off a little bit, and relaxing. But we do think very seriously about environmentally important problems. And we do this under the 2 different fields related to chemistry of photochemistry and electrochemistry. Okay, and so photochemistry, as the name implies, involves light driving chemistry, or even the reverse reaction of chemistry driving light. One of those, of course, would be solar energy conversion for solar cells and direct chemical conversion. And so that leads me into the second topic that my group studies extensively, is called electrochemistry, coupling electricity directly to chemistry. And while the word is called electrochemistry, that really means electricity. When one studies that, they must think about both the motion of electrons and ions. And that will come up in my talk today. I'm going to have a mix today of engineering aspects, real world reactor designs, techno-economics, big picture stories, and then also couple in a little bit of the basic science, because that's really what gets me and my group energized about coming to work every day. I want to start off, though, by actually going back to my roots in mathematics and introduce some general economics. Okay, and this is economics that we all know, so this isn't going to be too surprising to anybody, but it's painting a picture to get into questions related to global warming. And so I'm showing a picture here of my 2 children. They came and visited me in my labs. Again, I'm a photochemist and electrochemist, and so they were very excited about wearing the laser goggles as shown here in this picture. Both of my kids have expressed some interest in going into research. They say, "Daddy, I'm interested in the things you're doing. I think I might want to do this one day." Well, my wife and I realized if that's the case, they for sure need to go to college, right? And so if they're going to go to college, we need to invest some money. So let's say, as an example, we invested $1,000 when my oldest, was born. If we stuck that, we put that in the bank and we had a 5% interest rate, okay? Maybe it's lower, maybe it's higher. It's not important. The important part is if you compound this daily or continuously over 18 years before they go to college, we have some money, right? We have some money to send my children to college. Unfortunately, we don't have a lot, okay? $2,459 and some odd cents. But the point of this exponential power functions are ubiquitous in our everyday lives. Okay, and this is one example of them. This will come up throughout my talk, this idea. So let me keep going along this thread and take two little tangents. How can we increase this amount so I can actually send my kids to school? So one opportunity would be, what if in addition to $1,000, every single day I invested just another $10? Okay, that's 1% of $1,000, just adding $10 every day. And we did the same type of math problem. You very quickly see, wow, wait, that looks like it's an interesting strategy to get them to go to college. You know, maybe a private school for a couple of years, a public school for all 4. You know, I'm not sure about graduate school yet, but we can at least get this started. The take-home point is that small, consistent modifications on these exponential type behaviors can have impact. Okay, let me share one more here, and then I'll get into the story. I promise we're not going to have an economics lesson here the entire time. But what if I had a creative way that this $1,000 could actually grow by 50% interest? And I'm breaking it out to say, what if there are 10 different threads of ways to grow it by 5%? Well, now we're getting pretty amazing. Okay, maybe they could buy a small university or something. I don't know, probably not enough, but $8 million, right? We have tons of money. And so multiple exponential pathways can really accelerate growth. And this is a very simple story, right? This is, I'm going to say, simple economics, okay? So if we want to take this and apply it to other systems that have exponential behavior, things get a little hairier, okay? And so what I'm showing here is the roughly exponential rise of CO2 emissions. And I'll show you a lot of exponentials today, at least in the intro of my talk, to really get across the point that they're ubiquitous and that they can be influenced by even very small drivers, okay? And so what these data are showing are just over time from the start of the Industrial Revolution out to today, the fractionation of the CO2 emissions broken by different regions. And now I gave examples before about this 5% growth multiplied by 10. Well, that was on purpose. There are about 10 places listed here. And although it's hard to see, if you look at any individual like this green one, although it's going up and down, it is growing. Okay, it's growing over time. So when you compound those, there can be real consequences. Okay, so 35 billion tons today in 2022, and that has downstream effects that I'll also explain in a moment. Okay, and so this is kind of not a new problem or not kind of a new idea here. Jules Verne and the Mysterious Island had some text I'm going to read to you. I'll do this quickly. And what will they burn instead of coal? Water, replied Harding. They're going to burn water for energy. Yes, but water decomposes into its primitive elements, replied Cyrus Harding, and decomposed doubtless by electricity, which will then have become a powerful and manageable force. Yes, my friends, I believe that water will one day be empowered as a fuel, that hydrogen and oxygen, which constitute it, used singly or together, will furnish an inexhaustible source of light and heat of an intensity of which coal is not capable, right? Coal generates CO2. Someday, the coal rooms of steamers and the tenders of locomotives will, instead of coal, be stored with these two condensed gases, hydrogen and oxygen from water, which will burn in furnaces with enormous calorific power. There is therefore nothing to fear. Okay, the fear here was about running out of coal. We don't have a fear today of running out of coal, but we do have a fear of increasing the amount of carbon dioxide in the air. Sadly, we haven't installed many technologies that can do this today. So when this maybe was being read by Jules Verne in 1874, he was breathing in and out 285 parts per million per volume of carbon dioxide. As I read this today, and I'll read my quote, I'm scared. In 2021, I'm breathing in and out 415 parts per million volume of CO2. That doesn't sound like a lot, okay? And if you look at this exponential, you say, well, that's the only thing that's changed. The Earth is a complex system, okay? As many of my colleagues can tell you, I know Steve Davis gave a talk here. I'm sure he talked about some of this. These small changes make a big difference in overall outcomes to our environment. And even this net 1 degree increase that we've seen so far is having dramatic effects. Okay, so how do we mitigate this? Okay, enough background on kind of the problem. We need to mitigate burning of fossil fuels. In fact, cement production and other things create a lot of CO2. So what happens here, right? We end up putting a lot of CO2 in our air every year, about 35 gigatons. Now realize this 35 gigatons is on top of about already 3,000 gigatons, effectively, of the CO2 equivalent. So we're only adding about 1%. 1%, I mentioned 1% before, right? I said when we were investing in my kids' school, I wanted to add 1% every day. Well, this is adding, I don't know, 1% every year. that can cause big effects when you have exponential problems. Okay, so anyway, this is the amount of CO2 going into the air. Does it just sit in the air? Well, no, it doesn't. Some of it, not all of it, but some of it gets sourced into the oceans. And you might be saying, why am I showing this? Is this really a big deal? Only 8 gigatons out of an enormous supply of CO2 equivalents in the ocean are the CO2 is going there. So why is that a problem? Again, little things can make a big difference. And it turns out the problem is not the CO2 directly, but the CO2 reacts with water, H2O, to make these two species. Okay, this is baking soda, right? And this is a proton. So what it's doing is it's acidifying the oceans, and the oceans have very, very, very few of these. So if you even put 8 gigatons per year in there, you are greatly influencing this concentration and really wreaking havoc on the life and the ecosystem there. Okay, what else happens? Out of the air, the CO2 can go into land. How does it go into land? Well, it gets fixed mostly by plants. How do plants do that? Well, they use the energy of the sun, right? And that's going to be a theme of my talk as well, is how can we leverage the energy of the sun to mimic photosynthesis, to do things like plants do to take CO2 out of the air. And then moreover, I'm also going to discuss with you some ways that my group is working on taking CO2 out of the ocean. So really the conclusion here, how do you mitigate these issues? You stop burning fossil fuels and making carbon dioxide from cement production, and you suck carbon dioxide or bicarbonate out of our ecosystem so that you can undo ocean deacidification, remove the CO2 that's resulting in global warming, and those things. So again, that's what I'm going to talk about today. So of course, I am in a basic science department. My group I guess we mostly call ourselves so-called physical chemists. So they're kind of the chemists that think maybe the most about the physics of systems. And so I teach a graduate level class in photochemistry. And I took this slide right from those slide lectures, okay? And the question here is, why would one want to possibly use solar energy to power things that we do? Okay, and I have a lot of blurbs here. If you're really into it, you can read these. In fact, all the slide deck and even videos of me giving the class are available. If you want them, you should email me. But nevertheless, here's kind of an interesting take-home point. Light-driven processes between these things called black bodies. These are hot emitters that emit all sorts of different colors of light. They interconvert energy and work like heat engines and refrigerators do. Okay, so what does that mean? Okay, it means that the sun is hot. Okay, this is the temperature of the sun in the Kelvin units. Here's the average temperature of Earth in Kelvin. Because the temperatures are so different, you can efficiently take this energy and do something with it, okay? Do useful work like generate electricity or generate chemical fuels using electricity. So that's one reason why the sun is important. I'll get to the other reason in one second. But of course, every night, right, we don't see the sun anymore, right? We look up into the sky, and if we're staring at the universe, which is actually pretty cold, you can actually get power by exchanging heat with the universe. I'm just throwing that out there because it's something my group likes to think about on rainy days and on weekends, that you can extract power at night, okay? But you're able to get a lot more during the day using solar panels, okay? Now, here's another thing. There are more options than just solar power, right? You can also use wind turbines and get electricity from wind energy. There are technologies and designs out there to use wave energy. But where does wind come from? Where do waves come from? They're a trickle down from the main heat source on our planet, the sun. Okay, and so if one wants to harvest energy from wave energy, that's fine. If you find an economical way of doing it, by all means we should. But the maximum amount of power available, if it's driven by the sun, is necessarily less than the wind, which may be driving that, and then therefore also the wind is less than the sun. Okay, but it turns out we have pretty efficient, cost-effective ways of harnessing solar energy and wind energy. Those are two that are highlighted often, and that's what I'm showing on the plot here on the right. This plot is pretty dense, but I just want to go over it pretty quickly. The x-axis is on what's called a logarithmic scale. So these numbers are jumping by factors of 10 in terms of the cumulative installed capacity in units of power of these different ways of generating power for us. Okay, so solar photovoltaics, onshore wind, offshore wind, and some others, as well as now on this axis is the cost. Okay, and this is the levelized cost of the overall energy, also on a logarithmic scale. Okay, now this is typically how these data are plotted. If you plotted either of these over time, okay, either of these, the capacity or the cost, they'd both be roughly exponential. Okay, so what's happening is we're growing our installed capacity exponentially. Okay, this occurs because of something called economies of scale. As we build more, we end up building more again. It's an exponential function, and because of the economies of scale, the overall price also drops exponentially. So our current price here, at least in 2019, is this number here. I'm going to write it in these units, and this is a more recent number from 2020. So we can get electricity, okay, this solar electricity, for about 7 cents, important to know that, per kilowatt hour. Okay. The problem is not that this is necessarily too expensive, and lo and behold, this should go down, continue to go down as we have more capacity. The problem is that when we have too much solar energy, our grid, our electricity grid, goes quack. Okay, what do I mean by going quack? Well, there's something called the kind of infamous duck curve of the net load on a grid over time when there's a lot of solar and other renewables installed. Okay, so what does this mean? So a normal grid load, if you had no solar electricity going into your grid, would be relatively flat, meaning what is the amount of power we need throughout the course of the day? It rises a little bit in the evening, but it's relatively flat. When there's a large installation of solar panels like there are in these data here, you can see that over all of the days between the middle of March and the middle of April in 2020, there was a considerable dip in the amount of electricity needed from the grid. Now, where's the grid getting its electricity from? The grid's getting it probably mostly from burning fossil fuels and other things, but the grid doesn't respond as easily to this, okay? And so this is because people are not needing as much grid electricity because they have solar, and this wreaks havoc to the grid. Okay, that's the first thing. The second thing, which is probably even more important for this conversation, once we keep installing solar, we keep having more and more solar photovoltaics and more solar electricity, at some point, we'll have all of the power we need at high noon. Okay, but that still doesn't solve our problem of getting electricity at night, right? And so this is the fact that our supply and demand are coming at different times requires that we store this electricity, because the grid by itself has no inherent storage. Okay, so not only does California have ducts, New England has ducts, everybody has ducts. Okay, places with large installations of solar power have these so-called duct curves in terms of the load on the electricity grid. I found these data, for example, in New England recently at 2 different times of the year, because it paints an even a deeper picture about some of the challenges here. Of course, in the springtime months, the days are longer. In the winter times, they're shorter. But in the winter, around Thanksgiving, we actually typically, at least if you're in New England, you're going to be needing more power than in the summer. Okay, and so there's not just an offset from day to night, but day to day and seasonal and things like that. Okay, and so to store this energy, one option is batteries, right? We're very familiar with batteries. The challenge with batteries is long-term storage, like seasonal storage, and that really hasn't been solved yet in terms of an economical solution. Okay, and I'll get to that in a second. So when one wants to store energy for long times and not have it just spontaneously discharge, one often uses chemicals. And again, I'm a chemist by training, so I'm very excited to be looking at all the different molecules that have on this plot different so-called volumetric energy densities and gravimetric. So this just says, you know, per the volume of the liquid that you have, how much energy does it have is in it. So something higher on the list is better over here. And on this axis, per its mass, how much it weighs, how much energy does it have. Things on this end also have a lot of benefit. So just a very quick highlight. I'm a PI in the so-called Liquid Sunlight Alliance. It's a Department of Energy innovation hub. We are working on developing basic science ways to use sunlight to generate liquid fuels. But that's not what I'm going to talk about today. I'm going to talk about the other part of this plot, and to come back to what Jules Verne tried to stress before, that if we want to get hydrogen and we want it to be clean, okay, not emit carbon dioxide, it needs to come from water. We need to use electricity, have water as the input, generate hydrogen, also oxygen at the same time. And there's some definite arguments why one would want to use hydrogen for long-term storage and even transportation. Okay, so let me just wrap this part of the story up and transition into what my group's solution we think is to scale for getting clean hydrogen. Okay, and this comes from a very simple direct math problem that's related to targets the Department of Energy has set for goals by the end of the decade. Okay, and so the Department of Energy has set a goal that we would want to get to utility scaled solar electricity of about 2 cents per kilowatt hour. Remember on the previous slide, I showed you right now we're about 7 cents. It depends where you look. That's on average. This says we're about 5 cents, but nevertheless, the goal is to get to 2 cents. So what if you took that electricity at 2 cents per kilowatt hour and you used it to make hydrogen from water? Okay, that's a well-known reaction. It's called water splitting or water electrolysis, and it has a known energy. Okay, a known energy per mass or number of hydrogen molecules. It has a known a voltage you need to do this at ambient temperature, where you don't end up cooling your system. This is the so-called thermoneutral voltage that one would need. So you can convert these numbers into units that allow you to compare them or use the cost to get some information about what if electricity costs this, and if you were only requiring the absolute minimum amount of energy, you didn't have to pay for anything else. You didn't have to build a plant. You didn't even have to build the device. The device is free. Just from an electricity cost standpoint, how much would it cost to make this hydrogen? And the math is simple. You end up taking this number and you multiply it by this number, and you end up getting about, this should have said, sorry, this should have been cents. What am I doing here? 2 cents, 40. Nope, this is right. Sorry. 80 cents per kilogram of hydrogen. Sorry, I got nervous there for a minute. The calculation says it's 80 cents per kilogram of hydrogen. So why is that important? Because the DOE also came out of a recent target in their Energy Earthshot initiative for clean hydrogen that we want to get to $1 per kilogram of hydrogen by 2030. This tells me that minimally, if I'm going to use solar electricity at the projected cost of solar electricity from solar cells, that I'm already going to be at 80 cents per kilogram of hydrogen. Therefore, I have 20 cents to spend on people coming to work every day, building the system, and other externalities. And so this is going to be a really difficult challenge to meet. Okay, but we must be up to this challenge. We have exponential reasons to be up to this challenge. And so this is what I'll tell you about today, my group's efforts there. Why was this dollar set? Well, the dollar was set because there is a way to get hydrogen today, not from water, that releases CO2, and it costs between $1 and $2 per kilogram of hydrogen. So here's kind of the simple, I'm going to call it the simple picture. How would you do this? How would you take a solar panel and have it drive an electrolyzer just to understand that minimum, this 80 cents per kilowatt hour idea? Well, a solar cell, a solar photovoltaic is powered by light. After absorbing the light, you want rapid transport of something called an electron in a hole. They're the mobile species in this solid material. And importantly, in a solar cell, you design the solar cell to have a region that has an electric field in it that separates these charges, okay? And when you have that, when sun strikes the cell, you can get power out, okay? And that's actually shown with these curves. In the dark, the curve is exponential, and we have exponentials everywhere. In the light, this curve shifts down, and this is the power you can get out of this device. So the important thing I want you to take home from here is I'm drawing this shaded region as being this charge separating region that can get you this exponential curve and get you power. Okay, that's what you want out of a solar cell. Out of an electrolyzer, I can draw a similar cartoon, but I no longer have this separated electric field in the middle. You don't want this in the middle of your electrolyzer. Okay, if you had something like this, it would make your electrolyzer inefficient. But instead, you need to be driving chemistry. So at these electrodes, you would be driving hydrogen evolution and water oxidation into oxygen. It turns out that both of those reactions are generally exponential as well. So interesting, again, there's exponentials everywhere for different reasons. Electrolyzers have roughly exponential behavior, and solar cells have roughly exponential behavior for different reasons, okay? So what you can do is you could couple these. You can wire these together. You could maybe even do better. Okay, we could take something that looks like a solar cell that says PV1, PV2. These are two different light absorbing solar cells. These are now catalysts put on the surface. So each of these is an exponential that can generate power. Each of these are exponentials that use that power. And this is a concept presented by many, but I'm just highlighting something from a Department of Energy report in 2009 that shows this integrated photoelectrochemical design. Now, this design was meant to look like a solar panel with catalysts on it. It was meant to look a lot like an electrolyzer in a solar cell. So while the components can be manufacturable currently because we have solar cells now, we have catalysts, the overall design is arguably still not economical to get us to this dollar per kilogram of hydrogen that the DOE has set as a target. So the Department of Energy also simulated or analyzed the techno-economics of other designs. And so one could envision, instead of having something that looks like a traditional solar cell and electrolyzer, developing smaller nanoparticle-based solar absorber materials that hopefully act like diodes. Okay, we want them to have this exponential that gets us power, and put little catalysts on them that are hopefully inexpensive. And the reason that this idea is interesting, because these things still look a lot like this, is that the form factor for the overall reactor, the overall plant scale design, can be considerably different, right? This doesn't look like a solar panel or an electrolyzer anymore. It has its own challenges for sure, but now these are like big baggies in the middle of the desert, okay? And so it could be economical. And the idea would be that if you can make something that is almost as cheap as rolling out AstroTurf, consisting of things like this with small amounts of water, maybe there's a pathway to an economic solution to reach the hydrogen Earthshot and to mitigate the challenges of CO2. So there are definitely challenges in this so-called photocatalysis direction. Those are those small particles. Let me go back to this photoelectrochemistry idea. Sorry, I'll go here. The first design shown here that looks a lot like a solar panel with catalysts on it. I was part of a team that reported all the literature reports of the efficiency of converting sunlight into hydrogen through water splitting. The efficiencies are actually quite high. So the demonstrated efficiencies are high. So that's a plus for photoelectrochemistry. Unfortunately, the systems are generally not stable. And as I've already mentioned, they're really in the end unlikely to be economical. I was also part of another review paper also in 2015 that also then summarized the photocatalytic reported efficiencies in the literature. Unfortunately, photocatalysis, the thing that may be scalable, may be a scalable solution to global warming, are actually highly inefficient today. Okay, and so this axis is not efficiency, where the previous graph got points up to about 15%. This axis is called quantum yield. I don't need to get into details except to state that essentially all of these points being on this scale, you need to multiply or divide these numbers by about 100. Divide them by 100 to approximate the overall efficiency. So these are really inefficient systems. That doesn't scare me and my group. We're really interested in researching these because there is an economic pathway forward to getting cheap hydrogen. And I think this is definitely something I'm hopeful that others will be interested in researching a lot as well. And in fact, there are many groups around the world. In particular, this one is in Japan that has demonstrated a large-ish scale demonstration of photocatalysis. These sheets here are just essentially painted on nanoparticles on a sheet, okay? And they show that they can operate this, we'll call it plant, at less than a 1% efficiency, not very efficient, but nevertheless, this nice demonstration is starting to push forward this general idea of a scalable solution. One thing, or two things to note here. One is that during their tests, one of these systems actually cracked. Somebody dropped it and it cracked right down the middle, okay? But it still worked. It still worked because each of these little particles is like its own little reactor. It's like its own little photosystem in nature, in biological photosynthesis. So even though there's a macroscopic crack, the system still worked. And so that's an interesting advantage of this design as well. Now, this design in particular required post-separation of hydrogen and oxygen and actually co-evolved an explosive mixture. So there are definitely risks associated with this design. But what my group is working on is a different design. Okay, it's like the design I showed you a couple slides ago. It inherently has hydrogen and oxygen separation. We've been funded by the Department of Energy through their Hydrogen Energy Materials Network program for a while. I'm showing you my team over here of co-PIs and collaborators at national labs, the students and postdocs on the project, and then our additional collaborators on the project. So what we're working here is we're really trying to understand the theoretical and experimental limits to this photocatalytic design. What we've designed in this cartoon here is a kind of a different rendition than I showed you several slides ago, where instead of having these bags next to each other, they're actually stacked, okay? And the stacking provides advantages due to efficiency as well as transport, because these bags are meant to be very thin. It requires extra structural support, so I'll show you in a couple slides. This design is not scalable, okay, but we have new designs that we think are. But this design nevertheless taught us a lot of things, including some unique advantages that I'll share with you in the next couple slides. More recently, what we've been interested in is are there ways to use the heat from the sun to induce mixing in this type of reactor? So just to give a little picture here, we do have bench scale prototypes of these stacked reactor type designs. We're doing advanced finite element simulation modeling to understand how convection and mixing occurs in this system through our collaboration with Rohini Balachandran at the University of Michigan. She's in the mechanical engineering department. So let me just tell you some of the advantages of this system related to stacking. One of these very interesting observations we had about this, a unique aspect of this reactor, where each of these particles individually, these little reaction centers, just like nature, are not absorbing all of the light. Okay, these aren't very thick particles. These are nanoparticles that absorb some light and also transmit some. That's not how the solar cell works. Solar cells try to absorb as much light as they can as their energy allows. And so we've discovered some really unique aspects of having this type of design. There is a very big challenge is that in this design, there necessarily is an additional molecule one needs to add to shuttle charge between these reactors. So you need to have particles that are very selective in their reactivity. And I'm not showing data here, but we're working with arguably one of the world's leaders in selective reactivity and electrocatalysis, Dan Esposito, who's in chemical engineering at Columbia, who's developed just world-leading coatings to coat these particles and give them properties to allow them to have selective reactions. So anyway, let me show you some of our results about stacking, this unique opportunity, and then just some really basic science things that we've learned. Okay, so some key discoveries include, as I already said, stacking these reactors. So one of the questions we had at the outset was, could this reactor be as efficient as this photoelectrochemical design? This thing that looks like a solar panel, kind of maybe wired to an electrolyzer or integrated. And so there are well-known physical equations one would start with to analyze this. And guess what? They're all exponential. They show up everywhere. There's an exponential here regarding the penetration of light. There's an exponential here. This is the one that tells us about the solar cell, how good of a diode it is. This is the exponential that describes the electrocatalytic part of the system. So if you put these together and you just analyze what the maximum efficiency can be, we've shown that under the right conditions, if you choose the right molecules with the right properties and right materials with the right properties, your efficiency can be as large as a photoelectrochemical system. That is as large as a direct wired solar cell to an electrolyzer. So I won't go into details here. You can read the paper if you're really interested, but to keep this at a little higher level, we'll move on from here. In addition to these physics, and in this model here, we've added more, okay? We've added, okay, not necessarily exponential physics here, but this talks about transport of species, very important in this reactor. We have to think about transport. And in doing so, our collaborators have run simulations to suggest to us that we can, in an optimized reactor that's just based on diffusing materials in the reactor, that we could reach a 10% efficiency. Okay, and so that was exciting to us. Now, this is in the absence of any mixing, any of this thermal convection I showed you on the previous slide. With thermal convection, this number can go up. So this is a completely passive kind of autonomous device, and that was interesting for us to discover. So let me tell you really quickly this little story about incomplete sunlight absorption. I've already hopefully stressed that this is my little cartoon when you have a diode that makes a good solar cell, and this is kind of some quantitative metric of its exponential performance. If you take that and you add that to an electrocatalytic system that also has kind of exponential performance for doing chemistry, you can begin to analyze, if you have these data and these data, what the overall performance of your system would look like. So let me just show you as an example here. If you took this curve in the light and you plotted it, you have to shift it a little bit, but you plot it on the same curve as these data, you're able to predict where the whole system would operate. So that's what my group did. So the black line here is this analogous to this green line here. The blue line here is analogous to this, the behavior describing the electrolyzer. So the way that you, mathematically, the way that you predict the efficiencies, you just see where these two overlap. Essentially what it's saying is that this is driving reactions at a rate. We want to know when it's driven at that rate, what its behavior looks like. And so that's what that point represents mathematically, where those two functions are equal. Okay, so if you go to that point, it predicts that you get a current density, which is close to the efficiency of about 9. So the efficiency of this is about 9% efficient under this simulated condition. So here's the interesting idea. What if you took your light absorber and you cut it? You just literally pretended you cut it into 8 equal pieces. same amount of material, 8 pieces, like individual reactors, each with catalysts on them. What you would now have is this same catalytic performance, but you'd be seeing where it overlaps with each of these red curves. Okay, these red curves stand for the power generated by all the little 8 slabs as you go deeper in the reactor. So you just take where they all intersect and add them up. Okay, and so if you take those points and you add them up, you get a bigger number. Okay, so the conclusion here is that instead of having a single slab of material like we always do when we make a solar cell that absorbs as much light as it can, if you cut it into many little materials and have it directly drive chemistry at its surface, you can actually get a larger efficiency by having more absorbers. So if there's an economical way to produce the absorbers and make the materials, in fact, we predict that your overall theoretical efficiency as a function of the energy of the actual light absorbing material can increase considerably as you have more and more simulated number of absorbers. Okay, this is a really interesting, I think, conclusion from this work. So let me wrap up on this last little tidbit. I'll show you some pictures now, right? We're working with Xiaoxing Pan, who's at UC Irvine in the physics department in material science and engineering, to actually map out atoms in our nanocrystals. We're trying to understand why these don't work efficiently. And so to do that, we're taking high resolution images. This scale bar here is about 1/10,000th smaller than a hair, like a human hair. Okay, so these are very tiny pictures of our nanocrystals. We, along with his group, can use high resolution techniques to actually measure single atoms in the lattice and find where the dopants are. And we have really interesting observations from these that are helping us paint a picture to explain their performance. What we're also doing is we're not only taking cartoons of single particles with this coating I mentioned before on them, we're running simulations to understand the dynamics of how these operate. And with our collaborators at Sandia National Lab, we're actually measuring the performance. We're measuring the diode performance of single nanocrystals, single particles. This is a big tip that's coming down and touching the particle. We're measuring the behavior. And interestingly, the particles aren't simple diodes. They're not simple exponentials. They have 2 exponentials. And what that means is we're learning why these materials don't work. Okay, enough of the basic science. Let me come back to the big picture. So I haven't told you yet the details of whether this design is even scalable or techno-economically viable. So I'm going to walk through a couple slides of data that was generated by our collaborators at Strategic Analysis, who performed detailed techno-economic analyses of several different designs that we came up with, and we converged on the design shown at the right for a plausibly scalable reactor to take sunlight and directly make hydrogen from water using these little nanoparticles. Okay, so what we did is we really piggybacked our thinking on existing technologies. These are so-called algae raceways. You have these big kind of reactor vats of algae that can be taking sunlight and driving different chemical processes for you. So we thought this design looks a lot like that. Let's understand from the economics of these larger scale designs. One of the take homes is that if you have one of these systems that we're trying to produce hydrogen from, if you want to produce about 10 tons of hydrogen per day at a 5% efficiency, you need to cover 30 acres. Okay, and so this is a big design. Okay, this is something that would be, again, we're hoping scalable, but over very big areas. Okay, the general design is shown here, where instead of stacking these little kind of reactors formally, each of the reactors, the separate reactor compartments, are tubular in form. Okay, and so this is a tube running through this material where particles would be in here. They're connected by these little bridges, and so I like to picture this looking almost like a flotation device, a flotation, like a raft in a pool. Okay, this is like a raft floating on the top of a very shallow pool. So we'd have particles here driving hydrogen, particles here oxygen. We'd have ways to collect these, and so the take home is shown here. When they perform this techno-economic analysis as a function of the lifespan of the actual system, they can project based on cost projections of everything I just showed you. As a function of the efficiency of the system, what would the cost of hydrogen be? To come back many slides ago, we're trying to target $1 per kilogram. That's what the Department of Energy is asking us to do. Here is $2 at a 7.5% efficiency. Here's $1.75. There's definitely room over here to plausibly get to this $1 per kilogram of hydrogen. And we're not finished running these techno-economic analyses. These are unpublished initial values. We think we can cut corners other ways as well. I'm not going to get into details here, but one of the major costs is actually the hydrogen compressor, because we're looking into ways to decrease the cost of that, use a single compressor for more bags. That would further shift the cost down lower for all of these efficiencies here. And the trend suggests that we could actually plausibly meet the hydrogen Earthshot. So looking at my time here, I'm doing well here. So what I'm going to do now is transition to the second part of the talk, which is significantly shorter, but I'd say it's an equally important aspect that we're working on in my group related to mitigating CO2. So I've described to you our efforts in what we think is a scalable solution for using renewable sunlight to directly generate hydrogen from water in a clean manner. That's one way to mitigate these exponential increases. A second way to do this, as I mentioned before, is to kind of pull the thing out of our environment, right? Take CO2 out of the air, or even take CO2 out of the ocean in its form of bicarbonate. So I'm going to walk you through my group's efforts in the latter, and mostly with the aim of deacidifying the ocean. If one can do this, not only do we deacidify the ocean, but we have a point source where we can pull the CO2 out, we can capture it, we could do something with it, we could convert it into a product, but we're mostly focused on this capture aspect shown over here. So I just want to give you just a little bit of a technical picture of how one goes about doing what I just showed you on the previous slide. Okay, and so the way that one can take bicarbonate out of the ocean is actually by adding a little acid to the ocean, okay, a little bit of a proton source. So we need to think a little more creatively about how one could use renewable electricity to make acid. Okay, that's not typically how we get our acid by electricity. Is there a way to do this? And so the start of the story actually comes back to the electrolyzer I showed you before, but intentionally putting a component in the electrolyzer that looks a lot like a diode. Okay, this looks a lot like a solar cell the way I'm drawing this. There's an electric field in the middle of your electrolyzer. Now this is going to mean the electrolyzer is not efficient. It's actually a better diode than anything else. And in fact, my group has made, I think, some of the best, we call them protonic diodes around. We're working in a project of the Department of Energy to make these protonic diodes. Just a little tangent here. I want to share something very exciting. Jenny mentioned at the beginning that I was named an inaugural Moore Inventor Fellow for the idea shown here. We're trying to make actually light-driven proton pumps using our protonic diodes to directly desalinate water. Okay, and so we have ideas related to this, to drip irrigation and things. I just wanted to put the highlight out there. I've given a general audience talk on this before if anybody wants to watch it through the National Academies. It's on my website as well. Sorry for that tangent, that little selfish plug there. But to come back now, okay, I'm going to tell you how you can actually make acid and base with this design, okay? And so to make acid and base with this design shown here, you need to make it a little more complex. Don't try to follow this. Don't follow this. The point is, if you feed seawater into something with this structure, with things that look like this, you can make HCl and NaOH. And that is the key step to taking bicarbonate out of the ocean. Okay. Now, the problem again is you have this diode in your circuit, so you have to work really hard to actually break this diode. My group has been working hard on that through funding in the Department of Defense to get more conductive behavior from our system that looks like it should be a diode. But here's the conclusion. We want to add acid to the ocean to drive out CO2 from bicarbonate. Well, what am I talking about? Why are you going to add acid to deacidify the ocean? Well, you've probably seen something like this before. Okay, and so what this YouTube video here is a picture of a demonstration of how one can get CO2 out of water with bicarbonate using acid. Vinegar is the acid. Bicarbonate is shown here. I can't click this anymore, sorry. Just baking soda and vinegar, right? This is the reaction that we're looking to focus on for our scalable solution. So the person showing us how we can make this volcano, I'll try to speed this up here. You better paint your volcano if you're going to make this demonstration. But the take home here, right? We're taking just baking soda, which is the bicarbonate, mixing this in water. That's the simulated ocean water. Why not add a color to it so we can see this, right? We've probably all done this in undergrad chemistry class. We pour this into our volcano. Then we take the vinegar, and they're adding color to it as well. The vinegar is the acid. Okay, you pour it in your volcano like your ocean, and boom, right? There is what we're trying to get to happen in the ocean. Okay, we don't want it to come out that vigorously. We need to control this, but the general design is that. And so here's a picture that collaborators of mine have developed for a new startup company that they're forming based on this idea, using electrodialyzers to generate acid and base, using the acid to take ocean water in, add the acid to the ocean water, have it degas out the carbon dioxide as a point source, take that degassed ocean water, add the base back to it, and put it back in the ocean. Okay, it's a closed cycle where you never actually add any net acid or base because you always neutralize it. And the water going back to the ocean, since it's removed its carbon, it's also removed that proton, it is more alkaline here. Okay, so not only have we removed the carbon as a point source, we've deacidified the ocean. Moreover, this part of the ocean is actually a better sink for further carbon dioxide. Okay, and so just to wrap up here, my last couple of slides, the Department of Energy has actually not only indicated the hydrogen Earthshot, but also the carbon negative Earthshot. They've indicated, I think, a third Earthshot on a long-term electricity storage, but the carbon negative Earthshot is looking to get to $100 per ton of CO2, a technology to do that in the next decade. We performed techno-economic analyses on our design of generating acid and base and using this CO2 stripping membrane contactor, and we have projections to get to this cost at scale ultimately. Just on my last couple slides, one of the interesting take-homes from the techno-economics is that from the electricity cost of the electrodialysis cost is the largest component of that. So we want to make the most efficient electrodialysis system we can by developing next generation membranes that operate more effectively and more efficiently generate acid and base. In terms of capital cost, the largest capital cost is actually for the membranes to strip the CO2 out of the ocean water. Okay, that complex change has to happen over a very large internal surface area. So there's a lot of cost for these materials. So if one can generate more effective ways to do that, there'd be possibly a scalable solution. So on my last slide here, I'm going to just show you very quickly some of the work that my group has been doing on taking these gas liquid contactors to extract CO2 from the ocean. One of the state-of-the-art membranes is from PermSelect here, which consists of these hollow fiber tubes. The tube is about the size of a human hair with a thin membrane on the outside. If you pull a vacuum on the inside and flow ocean water on the outside, what you do is you can suck CO2 through this membrane. And so CO2 is coming from that bicarbonate. We mentioned before we want to add a little bit of acid, but one can also speed up that interconversion of bicarbonate and CO2. And the way that we've been inspired to do this is actually from natural systems. There are enzymes in nature called carbonic anhydrase. There are a class of enzymes that can speed up that reaction by up to a factor of 10 million. They consist of this protein that has in its pocket a zinc ion. Okay, and so it's been actually known for a long time. Many inorganic chemists, and I'm trained as an inorganic chemist for my PhD work, have made molecules as mimics of this and shown fairly large enhancements. We're working to integrate these catalysts into these types of systems here, and we've already demonstrated in my lab an enhancement of the bicarbonate CO2 conversion by including these synthetic analogs of natural systems. So with that, I'm going to wrap up here. Thank you for listening. I'm happy to take questions. These are the different places that CO2 goes. I really think we have a plausible pathway in the next decade to be working on stopping the burning of fossil fuels, and we're going to work hard and see how far we can get. In terms of carbon negative and taking CO2 out of the ocean, I think we have some interesting plans there as well. And through this startup company that my collaborators have formed, I'm hopeful that we can meet some of these metrics. So on my very last slide, I do want to come full circle and say it's impossible to deny that exponential trends are all around us. Okay, so there are many exponential behaviors where small things matter. Okay, and I would really say, if before I do a deep dive about investing in my children's college funds, I'm going to talk to an expert who's been trained a little more in the details of those exponentials to make sure I get it right. And the same thing, I would argue and hope that people trust in scientists and engineers that they have thought very hard about their exponential trends and their models, and they're telling us very good information about things we need to pay close attention to. And that includes burning of fossil fuels, of course. Right now, that is the most economical form of energy, but we can maybe mitigate global catastrophes by doing certain things. I can beg you all to speak up, okay, to make claims to others, to tell politicians and such that we really need to be making these changes, or help out individually by reaching out to me and my group and asking how you want to be involved. Of course, we have government policies that mandate things, and we can have government subsidies or taxes to help with this problem as well. We need those. Okay, we need all hands on deck, and all approaches should be options. My group in particular thinks a lot about the techno-economic guided research and development. We think about what does the scalable device look like, and then we go back and dive into the basic science to try to get it there so we can actually have, hopefully, a solution that scales. Lastly, I'm very intrigued about if there's a creative way to modify humans so they can smell or see carbon dioxide. I mean, if we could see or smell that, I'm sure we'd get rid of it tomorrow, okay? So, you know, partially a joke here. You know, this is not obviously a picture of carbon dioxide, but it's other soot coming out. But if we had a way to do that, I think we get somewhere. And then very last, just to summarize again, my kind of first comment, when in doubt, trust the scientific method. Okay, if you don't remember the scientific method for grade school, please Google it, and then think about it. You use this every day in your life, okay, how you address any situation you're in. And we actually have an NSF grant to really promote the importance of the scientific method in everybody's life with middle school students and others, and I'm really excited to push that program forward. So with that, I'm happy to take questions. Thanks.
Thank you so much, Shane. That was a really fantastic talk. If you have questions, you are welcome to put them in the Q&A or raise your hand. Shane, there are already a few questions in the Q&A if you want to answer those.
Oh, I see him there. Yeah, great. Okay. Waman, hey, welcome. Thanks for the question. He said, thank you for the amazing, extremely well delivered presentation. Technical question, what is the current technology readiness level of photocatalytic hydrogen production technology? Yeah, excellent point, Plummet. So there's a scale, I believe, probably from 0 to 10 about the technology readiness level of a tech, you know, is the technology ready to be scaled up? When it's 10, it's on huge scales. When it's 0 or 1-ish, it's kind of an academic exercise at that point. I mean, I would claim, based on the demonstration from the group in Japan, that the technology readiness level is ready to be investigated on the large scale. I mean, I think the pictures I was drawing about these scalable, baggy ideas, I want to go out tomorrow and make those. Okay, we need to test those now and push them forward to understand engineering constraints that we don't know right now. They're just on paper and on slides. I would say we're at the level where we need to be building and testing devices and reactors. The efficiencies are not large enough from the particles. So is this thing ready to go big time to make cheap hydrogen? No, not at all. Okay. And that's where my group, and hopefully a lot of other groups, and hopefully a lot of investment comes in, because there is a pathway to an expensive hydrogen with high efficiency. And there's no fundamental limit in this particle system. Arguably, it may be more efficient under the right conditions if we develop better materials. So kind of a long-winded answer to say technology readiness is low, but it has a long, the chance for a big impact is high. So I think a huge amount of investment is warranted. So there's another question. Is that okay if I just keep going, Jenny? Okay. If the ocean leaks out carbon dioxide, would the leaked carbon dioxide then just be added to the air and contribute to global warming? Yeah, a fantastic question. Right. So currently, the concentration of CO2 in the air is larger on an energy scale. Again, anyway, the concentration of CO2 in the air is driving CO2 into the ocean. If we miraculously tomorrow we're able to pull a lot of CO2 out of the air with some capture technology like exists now that people are starting to scale up and taking CO2 out of the air, the oceans would be gas, okay, like that, kind of like that a volcano example I gave, except in the volcano example, you're adding acid to push the CO2 out. If you just pull a vacuum and it pulls the CO2 out, meaning you reduce the CO2 in the air, the CO2 coming out of the ocean is somewhat slow, but not insignificant. And so my colleague, Steve Davis, could actually answer this better. He sent me some papers that he's been involved in on modeling this very question. what happens if we pull a lot of CO2 out and we have a lot of renewables generating hydrogen and we don't need to burn fossil fuels? What does it do to the ocean and the entire Earth system? Excellent question. I think it's very detailed, and I bet there's a lot of exponentials. So I guess I can keep going here. Steve has a question. Good. Okay. Where would capture CO2 go? Yeah, Steve, we're not sure yet. There's a lot of places it could go. A lot of creative geological reserves and things I've heard rumors about. I am not intelligent enough, meaning I don't have the information to give probably a very accurate description at this time. I do know that capturing carbon and having that offset emissions from companies is very important right now. Okay, there are many companies that will pay a lot of money for getting the carbon. Okay, and so even if we have the technology today that eventually might get to $100 per ton, you know, today it's way more expensive. Okay, and so we need really an entry market. That's something that's very important, that you have some sort of niche market to get in while the cost is still high, or you have people, the will of the people that are just interested enough and want to pay the money and are going to pay for more expensive carbon. So that's not a great answer, to be honest, but you do need to do something with the carbon. And so conversion of the carbon to some liquid or solid product is good. Storage, right there are all these many options that you know. So I think you also mentioned compression, transport, and storage. Exactly. So you would have to compress it, and the compression cost is not insignificant. I don't remember the fraction of the overall $100. I believe it was like $20 per ton, which you have to add on top of the techno-economics that we're doing so far. But we do have projections that get us, I'd say, significantly below $100 per ton, as long as we have some innovation. Transport and storage, the hope is that with this ocean-bound system, there would be a clever way to do something out at the ocean. So there are still a lot of unanswered questions. And Steve, I look forward to our meeting shortly to talk about all of these. And then Plumman indicated, right, the technology readiness level is 2 or 3 and might be on the DOE website. I think the information I was sharing about the TVA is brand new. It's not reported yet in print. And so, you know, some of these things will be updated. So, okay, I'm looking at my time here. I guess PhD student in CBE department, Che Wan, thanks for your question. I have a question about the fabrication of photovoltaic catalysts, maybe perovskite materials. They're weak in water. Can you explain some strategies? Yeah, so there's a relatively new photovoltaic material been around, I'd say popular for about 10 years. These so-called halide, typically halide perovskites. And the perovskite means it's describing the crystal structure. So there's a lot of different perovskites. The halide perovskites will, from my knowledge, will almost always dissolve in water. I think there are some discoveries now where they don't always, but generally they're very water intolerant. And so folks working on solar cells made out of these halide perovskites have to think very carefully about water mitigation strategies. So to take a halide perovskite and dunk it in a big bag of water with catalyst on it is going to be even a bigger challenge. As I indicated, my team is working on coatings for selective reactions. We're also interested in those coatings to increase stability of things like perovskite materials. And I can also comment that the Department of Energy is funding projects to use these halide perovskites in photoelectrochemical systems where coating is very important, and they've shown some real promise. If you can put a thick coating of some silica or alumina layer on it, you can actually make them quite stable, but there's a lot of challenges. One little crack and the whole thing would dissolve, which is another advantage to the photocatalytic system. If one of your particles dissolves, maybe it doesn't matter because you have all these other particles that haven't dissolved. I think we're right at time, but there's one more question Sarah put here. Should I go for it, Jenny?
Go ahead, and then we'll make that the last question.
Sure. So Sarah's asking, are there possible location sites for CO2 capture from water that aren't the ocean? You're kind of reading my mind. Yeah, I've just started conversations with my collaborators about that. I was on a meeting this morning with somebody else to discuss, and we discussed that exact point. I think it's an excellent question to see if there are other sources of large amounts of, they call it dissolved inorganic carbon, bicarbonate and carbonate and other things in the water that aren't the ocean. I think from speaking with my collaborators, we think the reason the ocean has so much is because it's so big and there's so many rocks that have been weathering and releasing bicarbonate into the ocean. So you have to think of a place where the water is flowing probably across a lot of rocks. And so in terms of the techno-economic landscape of a direct, they call them direct ocean capture systems like the one I showed you, I think there are a lot of opportunities. There are opportunities from the R&D development side, because our models have suggested there are many ways, several ways we'll say, to get to the $100 per ton target, meaning you could make a really good electrodialyzer and have almost no innovations in the gas liquid contactor, and there's probably ways to get to that cost target. On the flip side, you can make a really effective gas liquid contactor, and then you arguably might not even need the electrodialyzer and things in between. So that's one aspect. The second aspect is, where would you put this? What does the economic landscape look like? I think the new company, again, started by my collaborators at Caltech, are definitely looking into that, and I don't have any answers.
Thank you so much, Shane. Those were all really great questions and a really great talk. There are other questions. I think Shane also has other resources, as he mentioned, if you ask him about it, about photocatalysis and other things. But thank you again for that fantastic seminar.
Thanks, Jenny. Thanks for having me.
Thanks to all the attendees. You'll have to keep updated about our next seminars in the next few months.